We now resume with lecture 2 on power flow of integrated power grid considering both transmission and distribution system of the day. Please join me in welcoming Professor Kamala Sadan sir once again for another session of valuable insights.
Yes, I'll yeah, I'll take it. Okay, so what we will it's my God, this was it. Okay, yes, it is fine. So what we will do is we will start from where we left, and then we will move on. Better, better. So what we will do is we will start from here and move on to the next part. So just a recap, what we did so far was talking about how to model the electric power grid with the inverter based resources under the knowledge of having inverter based resources coming into electric power grid, how to model electric power grid. That's what we were talking about. And one big change as far as the modeling, and then modeling also, we were saying that modeling we are going to talk about steady state modeling, right? Steady state means models are developed for to study the power capacity, right? Analysis, power capacity analysis. So that type of model is generally used for what we call it power flow analysis, right? So that's what we were talking about. Power flow meaning evaluating how the load is connected to the system and how the system behaves when the loads are connected to the system. So from that context, we said one big change that that happens on electric grid if we were to study the electric grid when the inverter based resources are connected is to have the electric grid studied together as a one electric grid. So you may ask the question, well, is the electric grid studied differently before? For power flow, we used to study the electric grid as power flow transmission network and power flow for distribution network sparingly, right? Now, if you want to have the inverter based resources connected to the electric grid, you must study the electric grid together of the power flow for transmission and the distribution network. So that was a premise. So what does that mean? It means that you need to run the power flow, you need to know the power flow, how it's been performed for transmission electric grid and the distribution electric grid, right? So now what is that study means? It means modeling of the devices and the devices connected electric grid. So what we did, we started looking at the models of electric grid for conventional electric grid. We started looking at the generator models, transformer models, load models, and that is for the transmission network, right? Then what we did? Then we started looking at the models of the electric grid, how that is represented for electric distribution system. Okay? So we looked into models of the electric grid, how is represented on electric distribution system. And in the electric distribution system, we said, well, it's unlike transmission system. You will look into what we call it as the substation connected to the distribution feeder. On the substation end, you will treat the substation as a voltage source, right? Substation as a voltage source. And then you have devices connected, and there are mainly two. So in the distribution network, your goal is to maintain the voltages on the distribution network properly, right? Why do you want to maintain the voltage properly on a distribution network? Because there are a lot of loads connected on the distribution network, right? So the loads are connected, the voltage will start changing. So you are maintaining the voltage properly. So you look at what are the devices that actually does that job to maintain the voltage properly. And we identified two main type transformers that's connected on distribution network that does the job of maintaining the voltage properly. One transformer is called, both are tapped transformer. One is called LTC or OLTC, which taps the transformer to improve or decrease or increase the voltage, looking at the looking at the load connected. That is called LTC. Looking at the load connected, which is a current, okay, of the load. Another type of transformer that is called tap transformer again, which is used to regulate the voltage, looking at the voltage on the load side and regulating the voltage on the source side. So there are two different. So the first one, looking at the current and regulating the voltage, is called LTC or load tap changer, OLTC. Looking at the voltage on the load side and then regulating the voltage on the source side is called voltage regulator, and it's also called distribution voltage regulator for on the distribution network. So we talked looking at both of them, and then you have devices such as capacitors connected to the points where the loads are connected. Capacitor also does the job of improving the voltage, right? Capacitor does the job of improving the voltage by changing having the capacitance value. There are two types of capacitors that is connected on distribution network. One is called, maybe you may not know, one is called fixed capacitor, where you take the capacitor bank or a can and then connect to the bus, which changes the voltage directly from capacitive reactance. So capacitor is not a device changing the reactive power. Capacitor is changing directly the voltage, changing based on capacitance connected to the network at that point. That type of capacitors are called fixed capacitor. There is another type of capacitors which is connected to the point to change the voltage, which are called, it's not variable, it's the same capacitor, but they're called switched capacitor. How does that work? It works based on switching in and switching out. So those capacitors are in or out. It's not varying or variable, but number or no number, right? That's like a switched capacitor. So switching of the capacitor can be done based on current or based on voltage switching or current switching. That's basically the capacitor and the load. And then you have the distribution lines. Lines can be 3 lines, 2 lines, 1 line, depending upon how the distribution network is plotted. Okay, so that's where we were. Good, right? Makes sense. That's where we were, and then what we were started looking at was looking at the equations for the power. We looked at saying that the bus variables are actually the voltages. Oh, we also talked about bus and node. Everybody's okay with that, understand, right? Bus variable is the voltage and the branch variable is the line currents and branch power flow. So there are, when you look at the our distribution system especially, we have two quantity. One is called the bus or the node, another is called the branch or the connected line. If you are talking about voltage, you always talk about the voltage on a bus, not voltage on a branch. You don't see any voltage. You have bus voltage connected to the ground point, right? Branches are actually reserved for flow. That's basically line current flowing through the branch or power flowing through the branch. We have bus voltages and branch currents. Branch current has, obviously, we said they are all in phasor representation, which means there is a magnitude and an angle, right? Remember, everybody in phasor representation, phasor means like a vector, magnitude and angle. And then you have a power flow represented in the form of apparent power. So the apparent power includes the active and reactive power. Active power in the active power domain and the reactive power along with that. So they are phasor complex phasors, right? Phasor representation in the form of a complex quantity. Make sense? So, so the state variables, when you look at it, are the voltages, and the branch variables are mainly the currents. And you can devise models. You just talked about the device model, how the models are developed for the device, and we also talked about how the models are developed for the DER and also the capacitor. Next, I think we discussed this. So good with the DER model. Okay, so then we said, well, if you are looking at a power flow model for a distribution network or for any system, there are two main equations for the power flow. First equation is called the power balance equation, where you want to write it down. These are the name of those equations. Power balance equation, where the power coming in is the same as power going out, is the power balance equation. And the second equation is basically voltage drop equation. So let's assume that you are looking at these 2 points. The voltage on Vj is equal to voltage on Vi. This is a mathematical representation. So I'm specifically talking about how do you write a math equation. Sometimes when you have a physical sense of how to do it, when you start doing a model or writing a paper, or writing a book, there is some there's a language that you speak when you say something. And if that's not the truth, then people will not understand. So you have to really specifically say the way that is written in the math. So for example, if you're looking at Vj, you say Vi minus Zij. Zij is impedance of the network, and Iij, that's basically the voltage drop. And Sij is what? Is that a power, injected power on a bus, or a power on a line? Sij is what? Power flowing through that branch. You see, it's going through that branch, not the power on. Yeah. For power, when you talk about, there are two types of power. One type is power flowing, whatever is for power flowing. Another type is power on a point, which is incoming minus outgoing. So you have to think about that. And then you have a power balance equation of Sij minus Zij, Iij, that's conjugate. That's basically I square. That's equal to Sjk plus Slj plus dr. So Sjk is basically the power flowing through from this branch to Jk, plus Slj is the power on that load on there, minus Sderj is a Der on that one, right? So what happens if there is no Der connected here and no load connected here? What happens to these two variables? They're going to be 0. So what are these equations? These equations are generally called generic equations. Generic equations are equations when you write after the equations are written, what you do is you develop an algorithm and then you write a software code, right, in MATLAB or some other script. So when you write a software code, you want to run that algorithm, you can write it in two different ways. One is to write it for a specific system, 3 equation, 2 equation, or you write it for a generic system. When you write it for a generic system, it's applicable for any bus or any node. So that's how you should write. So if you are looking at equation, you can develop that equation in a generic form or a specific form. When you write it in a specific form, you will be doing it for that specific case study example to understand whether you have written it right or you are troubleshooting and you are evaluating. You make a generic form. Okay. So if you are having this equation, this is a generic equation we call it, because these two nodes and the DR connected at this point are going to be 0 for this specific bus, and Sij minus the drop right there is going to be your power. Are you following? 3 equations, or either 2 equations and 1 derivative, which is apparent power equation. Good? Okay. All right. So with that being said, that's how the load flow is run for a distribution system. Now the question is, why do you need a load flow for a power distribution system? I think we talked about it. I just wanted to reinforce one more time. Load flow for a distribution system is required for what? Okay, for a conventional system, no idea, no integrated, it's conventional power grid. Do you want to run a load flow for a distribution system? Yes or no? Or do you want to run a load flow for a transmission system? Okay. You want one for distribution system? Why do you want to run for load flow for transmission system? Yeah, you can get the difference between the source and, but no, yeah, so the just to see whether the source is sufficient to okay, yeah, that's one objective. Source is sufficient to supply the load. What else? Why do you want to run a load flow? Angular? Angular displacement of what? The one of the main objective for the load flow is to get the voltage magnitude and angle of an electric grid. So the next question, why do you care? Why do you want a voltage magnitude and angle? Oh, how do you get the voltage magnitude and angle? By connecting the load to a specific point in the model and running the load. When you're connecting the load to a specific point, you are finding out the voltage at point. So if that load is changing, will you get another voltage? Yes, sir. Yes. So for several loads, you can get the voltage, right? So why do you care about several voltage, several load at one load and one voltage? Why do you care about that? Why do you need that? You understand my question, right? Why do you need that? Why do you need to run the load flow? That's actually a fundamental question. Why do you need a load flow? What is the purpose of running a load flow or power flow? You're not sleepy, right? What is the purpose of running a power flow? Huh? Understand the performance of the system. What do you mean by performance? What do you understand? What is the voltage level? So why do you want to know what is the voltage level? Very good. Yes, understand the voltage level, and it's the same thing that we said that the power flow is run to get the voltage magnitude angle. Why do you want that? So the reason for that is same thing as the water flowing through the pipe, right? You are trying to understand for a different load, what will be the voltage on my system? Is all the voltage good, right? Everything is excellent. If the voltage is not good, if there is a dip or higher, then what will you do? Okay, to understand that you can't the flow. Suppose the voltage is dropped or dip, what will you do? You can put a device on a specific location where the voltages are low or high to balance that voltage. For doing that, you need to know some tool. You need to have some tool to run. The main purpose of the power flow is basically that. Okay, it's actually done for the design, during design, suppose it's some or planning purpose or something. So planning purpose means what? You do the load flow again when the load is changing in future. Yes, you can do the load flow multiple times as a tool to understand what that voltage and magnitude is. So what we call it as the state variable for a load flow. When you run a load flow, is to know the voltage and angle of voltage. State variables in the load flow is basically now voltage and angle of voltage. So voltage is understanding the voltage is very important. What is another? We also said that if the resources are not correct, I mean the generation is not there. Obviously, the load flow will diverge, we call it, or will not work, or not give you results. So that's another thing which you get. What is the other thing which you will get from load flow? So another important thing, as far as economic standpoint, for the electric grid, everything is great, voltage is great, power is given from the source to the load, but how much power we are losing in the transit by when you generate the power from the generating source going to the load, how much power we are losing? Why do you want to know that? How much power you are using is directly proportional to money, and you want to know whether you can save some power to not lose that power. Two reasons. One, obviously money. Second is obviously you will get to generate a lot, right? So the objective of that power flow is, main two objectives are voltage profile and the losses, not having enough generating sources. If you do not have enough generating sources, obviously it will not work. But fundamentally, these are the main two things that you will want to know for the power flow. So power flow is used for planning purposes, and some of the things are written here. Power flow is used for planning purposes, and power flow is used for long-term operational purpose. How much voltage profile you have, what different load condition, and so forth. Load flows are also important if you want to supply the power through renewables. If you want to connect a renewable in a specific point, what happens to the voltage at that point? Will the voltage be great if the renewable has more power coming in? If the renewable has less power coming, will the voltage going to go low if the power is not proper? These things are important for the power flow standpoint connected with the renewables. So it's important to know, both the renewables are connected. So that actually is what we call it as VER or renewable integration studies. Integration study meaning you're connecting a renewable at some point. Oh, is that a connecting point of a renewable? Can you control the connecting point of the renewable? So a lot of thesis and dissertation you will see, it's called DER placement. Where do you place? Optimal location of DER placement. Optimal location of DG placement. Optimal in some other time in 10 years ago, there used to be something called optimal location of PMU placement, some device placement. Optimal location of device placement is great to do a study as far as an understanding is concerned, but it's not very feasible because the PV where it is connected and which location needs to be connected, you cannot control or you cannot guide. It is based on policy, it's based on where the land is, it's based on what the government says, a lot of other factors. So optimal locations are generally, it's a great theoretical study, but not very feasible. But after you are designing the locations, for finding out the location, what happens to the electric grid when the DER is connected? It's called DER integration study. Make sense? So analysis of impact on DER on existing system, you can do that as well. And what we generally call a smart grid study, which is I think it's a big word there. So I'll tell about that a little later. Okay. So that being said, we now understand the need for power flow and why we need to do the power flow. So now what we're going to do is we'll dive a little bit into a little bit more on mathematics and try to understand how you develop these models of power flow. So power flow in general are done in electric transmission system and electric distribution network. In electric transmission system, power flow is done as one line, treating all the three phases or three lines as one line. Okay. So that is generally called as one phase analysis, right? One phase analysis. Most of the time, those one phase analysis instead of phase power flow in transmission system, it is done on positive sequence representation. Okay. Why no negative sequence? Because there is no unbalance generally represented in the transmission system, and no zero sequence is no unbalanced represented in transmission system. So the transmission system models are generally called as positive sequence models. Those positive sequence models are used to run the power flow. What do you mean by positive sequence? Well, positive sequence is the same as all the phases power divided by all the phases power added together, or one phase power multiplied by 3. This is basically same as positive sequence. So if you convert from phase domain to sequence domain, and if the unbalance is not existing, positive sequence representation will be the same number as your phase representation. So you run in the positive sequence representation, so you don't have to do divided by 3, multiplied by 3, and then per unitizing, and then messing up with the number is not correct. All those things are avoided if you run in a positive sequence representation. So there's a group of power flow that runs on transmission system, mainly 3 of them running on transmission system, called 3 different ways of power flow. How many of you have heard these 3 names? First 3 on power flow. If you can raise your hands. I know you all are, but all of you. Can you raise first 3 names in this slide? These 3 names. Gauss zero power flow, Newton-Raphson power flow, fast decoupled power flow. How many you have heard these names? Not done anything. Heard these names. A few people have not. How many of you have worked on these all three, not developed code or anything, but have seen it, did some course around that, some level of knowledge for all the three. How many of you? Okay. So there is a knowledge gap. So I need to talk about transmission system. These are actually conventional systems. Right? Okay. How many of you have done at least one? So still there's knowledge gap. And which is neutral acid, causal and. All right. So we have three different ways that you run a power flow and transmission system. One is called. Can you read? Oscillatory power flow. Second one is called. Okay. Third one is called. Uh, so I'll, I think, take 10 minutes to just go through that. So the power flow models. Is that power flow models algebraic or differential? Is power flow models made of differential equations or algebraic equations? How many of you think that power flow models are based on differential equations? Oh, nobody? Yeah. How many of you are thinking that power flow models are based on algebraic equations? How many of you are thinking that power flow models are based on neither algebraic equation nor differential equation? Well, two people raise hands in both of them, I guess. Okay, are you? Is there any? Is that question not clear? Do you know algebraic equations, right? Are these equations algebraic or differential? Oh, these are power flow equations, we said. I mean, some form of power flow equations, right? Are they algebraic or differential? 100% sure, algebraic? How do you know it's a differential equation? What are the characteristics of the differential equation? You have a time dependent variable needs to be there in this. There is a time dependent, no time dependent variable. So they are not differential equations. They are algebraic equations. Are you thinking in your mind that confusing with nonlinear versus algebraic? Are they nonlinear or linear? Are these equations nonlinear or linear? Huh? How many of you think these equations are linear? There is no, by the way, I need all to raise hands, okay? No doubt. You be in one bucket or the other bucket. Don't stand in the. I cannot. Then there is no problem in saying wrong answer. I don't think there is any penalty for wrong answer, and there's only penalty for attendance. 90% attendance is required. That's it. There is no other penalty or credit for a wrong answer. So please say something. Whatever you. How many of you think they are linear? Whatever you see on the board. There is nothing part linear, part non-linear, okay? All these equations has to be linear if it is a linear one. All these some of the equations has to be non-linear to become a non-linear. How many of you think they are linear? Okay, how do you know whether they are linear? Okay, let me ask. I think that could be a reason that's why. Vi, one variable here. Is that a linear variable or not? Oh, complex and linear are different. They are linear or not? Huh? The linear, one variable. Another variable here, linear. Z, linear. I, linear. So is this equation linear or non-linear? So first one is linear. This one is not a linear, he says. This one is complex, but this one is not a linear. Is that linear or not linear? Linear? Non-linear. This power, this equation is not linear, he says. Is that correct? Everybody agree? Why it is not linear? Hmm? Which one multiplied? V and I multiply together. And if you multiply V and I together, then it's not non-linear. I mean, it's not linear. The two variables, you multiply the two variables together, then it becomes non-linear. What is the property of non-linearity, by the way? Oh, maybe a little interesting question here. What's the property of non-linearity? If it's a non-linear, then you will see a variable that is square or cubic or some, they are non-linear. Right? If the variable that is not square or cubic, that can be considered linear, right? If the variable that is multiplied by sine function or cosine function or something, it is non-linear, right? So now let us look at these two. Are they square? They are, is V square? Can you see V square? I square. So, and are they sine, cosine? No. So, are they linear? I'm actually probing these questions because this is important for modeling purpose. Huh? They're sounding linear, right? But are they truly linear? Are they truly linear? You understand my question, right? Or yes? So you react, whatever, react again. Okay, forget about that one. Look at this. Linear or non-linear? Non-linear or linear. Okay. So they are called power, right? See the power here. Oh, is this linear or non? Is this is this term has a square term? No. Is this has a square term? Has a square term? Yes. I times I. That's a square. Even though I don't say square, put two terms. Right? Here, this is non-linear, so the whole thing is become non. How about this now? It's a complex term. So if you try to treat that complex term in terms of uh, rectangular or Cartesian coordinate, then you will inherit what we call it as a cosine and sine function. Then it will become truly nonlinear. Let me not do that. I'm not going to write. Okay, I write it in the form of a polar form. So there is no cosine and sine, uh, angle and the magnitude. Will this become nonlinear then? Could be not. So what are the criteria? The criteria for nonlinearity is that you should not have the terms associated with that, right? So if you try to break that into separate equation, and you write two separate equations, then obviously you can treat it as linear equations. If you break it into, let's assume all these complex equations, we make it into two separate equations. Then they can be treated as linear. However, if they put it in Cartesian coordinate, still you can break it and put it in Cartesian or rectangular coordinate. Then it will become non-linear, right? So the other part is you see this VI conjugate, right? What is VI conjugate? Let's assume that you delete all the I and put V instead. So I equal to V divided by Z. So VI conjugate is V square divided by Z. Then it becomes non-linear. You see, right? But if you keep the I there and no complex connected, two independent variables, if both independent variables are independent variables and not dependent to each other, then you can treat them as separately and then you can write that separately. Why am I saying all these things? This is a trick that you may have to do if you want to do what we use called as optimization methods, which I think we are going to talk about it tomorrow. And especially some kind of a linearizing optimization method comes under the umbrella or the bracket called convex optimization. So nonlinear linear, making nonlinear linear is is an art, and you have to see whether you can do that or not. So we'll talk about it later. So right now you know that power flow equations are generally combine all the three equations are generally How many of you think they are linear? How many of you think they are non-linear? Okay, because we already said at least one clear evident non-linear equation sitting right here, right? All the three equations together. This one you can treat it linear or non-linear depending upon how you form it. How do you form model? You call it form model. I'll tell you a little bit about how do you form that model, how do you tweak it, and then how do you move it around. What are the ways that you can? So they are actually non-linear. Okay, they're non-linear algebraic equations. So nonlinear algebraic equations do not have a closed loop form for solution. You know what a closed loop form means? Analytical form, closed loop form, analytical solution. You know what analytical solution means? 3x is equal to 7. What is x? 7 divided by 3. This is called analytical closed loop, meaning you can directly manipulate those equations. 3x square plus 2x plus 3 is equal to 17. What is x? You have a quadratic equation in a derivation, you can solve it. They are called analytical form. Now, linear models are not, can be solved in closed loop form. So how do you solve it? How do you solve the nonlinear models? Are you following with me or are you stuck? You have nonlinear models, algebraic models, you cannot solve in closed. How do you solve it? You have to solve using iteration. What do you mean by iteration method? You know what you do? You guess. Yeah, you guess and check. Then you adjust your guess and check. Not trial and error. Trial and error does not have any method associated with. Iterative methods have guess and check. Are you following? So these are actually three methods to solve the power flow. They are all nonlinear solution methods, and they are using the method of what we call it as guess and check. One classical representation of solving a nonlinear equation is using a method proposed by Newton, and that's called Newton's method. Okay, this Newton's method, what it really does is you find the gradient of a vector or a phasor, and you go in the negative direction of the gradient of that vector to find the solution. So gradient of that vector can be found and can be gone into negative direction if the gradient of the vector is generally linear in nature. If the gradient of the vector is linear in nature, you go against negative slope of that linear function. Negative slope meaning depending upon the slope. If the slope itself is negative, then you go positive in the opposite direction of that slope, and then you will be able to find a solution. That is what the Newton has proved, and that is called the Newton's method. And Raphson, another engineer, connected together with Newton, then developed a method called Newton-Raphson power flow method. Similarly, Gauss-Seidel and all that. So what I'm going to do is I'm going to pick one method, Newton-Raphson, and fast decouple, and probably go through that with you in a very fast form. That's not a part of it, but so if you wanted to run the power flow method, you are going to run the power flow method nonlinear equations. That is basically what we are doing. We are running the power flow method in you can also participate, or don't know whether you are part or not part, but after some time you become a part. Education is always like that. Newton methods, if you run it, you will run the methods to solve the nonlinear equation. Now let's look at a nonlinear equation. What are the nonlinear equations that you have? Apparent power. Apparent power can be written in form of two quantity. One is active power and reactive power. So you have two equations, active power and reactive power. Is active power of a I think you already know this, but some of you may be a little bit bored because you might have heard this. Some of you may be teaching those, but I'm just going to reiterate. Active power and reactive power. These are the two things that if active power and reactive power on every bus, you should know. Right? Can you find the active power and reactive power of every bus? For some bus, yes, some bus, no. I make a statement like that. What does that mean? Let's suppose I have a load connector in this house or in this building, and the load active and reactive power is known to you, connected on that bus. What will be the active power and reactive power on that bus? That load. which is known to you. So do you want to do any math to calculate that power? You already know that. You see, but there is a bus, there is no load connected. I don't know what an active power and reactive power is. Do you need to calculate it? Yes, I need to calculate. So for some bus, you need to have an active power and reactive power known. Some you don't have an active power and reactive power. Okay. What are the other things which you should know to solve the power flow? We can actually solve it looking at it here. So there are two ways you can write the power equations. Everybody know that? You can write the power equations. Current power S is VI conjugate. In fact, three ways. VI conjugate. Can I write apparent power in another equation? V square divided by Z. Is there another equation that you can write the I square times Z? These are three different ways you can write the power. Same power, right? What does that mean? Power is obviously, need to calculate, right? So I can represent the power which is not known, S, which is P and Q. What else I need to know to solve it? Let's assume that I represent in terms of voltage. I need to know the voltage, V square divided by Z, solve it. Voltage, when I mean by that is, I need to have a voltage and angle of the voltage known, right? Because they're two different quantities. So how many variables I need to know? P, Q, V, and angle of the voltage represented as delta. So you have four variables I need to solve. And how many equations I have? Active power equation and reactive power equation. So how many equations you have? How many variables you need to solve? So there is a challenge. In general, if you have two unknowns and two equations, then you can solve that equation. If you have four unknowns and two equations, you cannot solve that equation. So there is another challenge. One challenge is it's non-linear, and we will solve using iterative methods. Assuming Newton has developed something, we'll go with that. Another challenge is these are two equations. No. So how do you solve that challenge? So people will come up with a trick or a physical system related trick. The trick is that if I know the load connected to a bus, for all the buses where the loads are connected, I assume that P and Q is known. So what do I solve? V and delta. Okay. So I have two equations, two unknowns. What happens for a generator bus? When the generator is connected, I assume that the power from the generator going out is known or controlled. Actually not known. There is a device in the generator which controls the power going out from the generator. What's the name of that device? A controller in the generator that is controlling the power going out from the generator. What's the name of that controller? Somebody. I have two choices. I'll only pick the wrong one. Right? There's only two controllers in the synchronous generator control. Only two controllers. What are the name of those two controllers? What are the name? Huh? What? Automatic voltage control. Automatic voltage controller is connected to a box in the generator called excitation system. Excitation system, automatic voltage generator. That's one control. What's the next one? Load frequency control is not done at a generator. Load frequency is controlled at the system level. To get to load frequency control, somebody is doing control on the generator. Who is making frequency 60 hertz or generator runs at synchronous speed? The second controller in a generator is called governor. Governor is the one who governs or controls to make the speed of the generator constant when the speed changes. So will the speed of the synchronous generator changes? Ideally no, because it's synchronous speed. But when the load is changing, the generator is not able to supply the load. So load is here, generator is here. For some time, the speed wobbles. So because of that wobble in the speed, this box called governor sense that and open the valve for the generator, pushes more fuel to the generator from the generator to maintain the power from the load equal to the generator. This is done in 3 seconds. That's the response time of the governor. So these are the governor is one controller and the excitation system area. What does it what? The governor is controlling what? Power, voltage, frequency. Governor is controlling. Governor is not necessarily controlling frequency. Governor is controlling speed and the power coming out from the generator based on the speed. Who is controlling the frequency? All the layer together, load frequency control and everybody together. Layer meaning there are different layer. Above the generator, there is a layer called automatic generation control called AGC. Then there is a layer called load frequency control. This is basically done with AGC and some other things called tie line control and all that. It's like a story, it's not a part of this course, so we're not dealing with that. But the governor is used only at a fundamental unit level to control the speed as well as the power going out from the generator. And the excitation system and AVR is controlling what? Voltage at where? At the terminal of the generator, where the generator. Oh, will this AVR and excitation system control the voltage at my home? Because it's important. I'm just saying that is because for so it once controls the voltage and one controls the power. So what is our thinking? I'm thinking that active power and the voltage I know. Why? Because I control. So if I know active power and voltage, I can calculate the reactive power and the angle for the generator. So you may ask, oh, all the buses are generator and the load. Is there a bus without generator and without the load? Yes, there is a bus without generator and without it. Do I need to calculate something on the generator? Hmm? No, that's a different. Do I need to control the power on a bus that is no generator and no load? Do you have a bus with no generator and no load? Yes or no? Yes. Yeah. So why you're I don't know. So do I need to know some variable? Well, if you have a generator with no generation, no load, such bus we call it pseudo bus, meaning those bus power coming in and power going out. You can write the power balance equation. You don't need to do any math to do that. Now we also have a problem. What is the problem? This is great, but who will take care of the losses on the electric network? How do you know the loss power? If you know the power of the losses, power for the losses rather, I can take the number and add it to this math and I'm done, right? Who will take care of the power for the losses? Do you know that? You don't know that, right? So the power for the losses means what? P and Q. There are two losses, right? Actually, so there is a loss term that needs to. So what you do is that we say that one generator will take care of the power for the losses. That generator, we call it a highest generator, and that generator is the one who is delivering all the losses in the world. And you will, for that losses, you will know that P and Q is not known and V and delta is known. That one single generator is called slack generator or a slack bus. Is one generator supply the losses on the entire transmission network? Do you believe that? I also don't believe that. So why did we make that? We make that because that's the only way we can solve it. So it's not realistic. It is just for method of solution. Now, if it is not realistic, do you believe it? Do you know how it will be correct? It is not realistic, but it is close to real. The reason is highest generator or largest generator will supply most of the losses. So 70-80% of the losses may come from that generator. The rest will be taken by other. So these solutions are not exact. If you go and to check it in the real life, it's not going to be exactly true. Is that okay to have a solution given by the power flow which is not exactly true? Yes, it is okay because we are using this for planning purposes or some studies. We are not using it to find out the changes in every dot with respect to time. So there are methods that people are going out from there and solving that problem to what we call it as distributed generator problem and all that. So we solved two things. We solved the nonlinearity thing using Newton's some stories about that, and then we also talked about how to write two equations and corner. So there's three different ways you do that. You understood what's going on in here. So you have power balance equation written. Oh, so now that same math that we represented before in the slide, you started writing that math in the form of that math you see there is written S. What's the first change you see here? Instead of S, it is written E and Q. Why did we do that? Why did not we stayed with S and then moved to P and Q? You just said, huh? Why? Why do we need active and reactive power? We need two equations. Remember, then only we can solve. So we represent the same one as equation into two equations. Okay, we did one more thing. What did we do here? As S was V times I conjugate. Remember that S, right? V times. Is there an I here? No. What did we do? We changed the V times I conjugate to V square over Z representation. You see V and Z. 1 over Z is Y, you are representing that, and you call it Y, so generally we represent as a Y bus, if you may recall. V times V divided by Z or Y, and you represented that in here, right? And we did one more thing. What did we do here? We break this into P and Q. We wrote this in what form? Complex number is written in what form? Rectangular form or Cartesian form, where you do one as cos, another as sine. P plus jq is cos plus j sine. This is called Cartesian representation or rectangular representation. Can you represent that in the polar form? Everybody know polar form, rectangular? I cannot go to that level now because we need to move. Polar form is a magnitude and angle, so this is represented in. So three things you will notice in this equation. One is 2 breaking into 2 quantity. Second is writing in the terms of voltage and Y. And the third in the form of Cartesian. Okay? So this is very suitable for power transmission network. Why? Because in the power transmission network, you don't really talk about the flow of current on the like a distribution network. You can keep the voltage and then solve using node voltage analysis or voltage analysis. So it's very good in representing that. Now what you do is that you look at the power balance equation. This power balance equation was there, which is calculated power minus scheduled power, and calculated power minus scheduled power should be equal to 0 along with the losses. And then the change in the power is what you use that as a mismatch. So how do we solve this? You solve the change in the power and look at the change in the power. First time when you start it, the change in the power will be too big. Then you guess, check, guess, check. Go to the change in the power, find the gradient of the change in the power and go in the negative direction and solve it. So we have a conceptual idea about that. So what we will do then is since we don't have a lot of knowledge there, I will go to my backup slides and I will show you. I was not planning to discuss about this, but I'll take 5 minutes, not more than that, because we may not reach there, to solve about the Newton-Raphson. I'll just stick with Newton-Raphson, maybe some derivative of other power flow. So this is basically a Newton-Raphson power flow in a network which has got voltage and current going out, and you represent the current in the form of Y times V. and Y is called the Y that we saw there. V is called the V of the node or the bus. Okay? So if you wanted to do this, you need to know the power flowing through the network using KCL. So you say the total current injected is equal to the current flowing through every branch. How many branch you have? Whatever branch you've connected to. And the total Y is going to be 1 over Z, and you can call that, each Y is going to be 1 over Z, and you can call that. I hope and this side you are able to follow what I am talking about. I am seeing from faces that some of you are punching out, but I have to move fast. So hopefully you will be able to. If you have, you are completely zoned out, you got to raise your hand so I can help you with that. Are you following? Are you following? Oh, they okay. So they are not in. So you can leave them. And other people, are they following? Are you following? So so that is so what we are doing here is we are writing the form of V and Y, and we are representing the power flow in the form of V and Y. So you see that in here, how you can represent that is by collecting the KCL equation for a 3 or 4 bus system. You can write the KCL equation in the form of I1 and I2. Current going in is equal to current going out. So you can write current going in is equal to V times Y plus V times Y. Is that easy to read? Is a complete pure Kirchhoff's law. And what happens? There is no current flowing in. This is very easy to write. You don't have to current flowing. You can write it 0 and then you write the equation. So what you do is that you collect the currents in the form of y v times y, and this y, small y making a big Y is called Y bus. Okay, and Y bus is a representation of all the small y's in the system. The KCL equation, you can expand that into the Y bus just by looking at it. How do you look at it? You look at the diagonal elements and you add all the diagonal element y's together connected to that node. Of diagonal elements are negative, y is connected on that. So with that, you can actually get a complete Y bus. And after you get the Y bus, you can write the nonlinear equation that is coming from expansion of the nonlinearity with the change in the deviation, and based on what we call it as a Taylor's expansion. I don't know whether Taylor expansion or Taylor series expansion you might have heard in your undergrad. What is a Taylor series expansion means? It means that any higher order system can be represented in the form of change of that function with respect to the change in the variable. These are not a differential equation. These are okay. Why they are not differential equation? Because there is no df divided by dt. They are not time differential equations, but these are change with respect to the function with the variable. So change with respect to the function with the variable is generally called sensitivity. Okay, change in one variable function with respect to the variable. So these are sensitivity equations for each of them. So what you do is that you get a higher order derivative. So you kind of ignore this part, and you ignore this part, then you have f of x 0 and then this delta x. So if you do that, ignore the higher order part, you can find the change in the x by looking at the change in the c divided by the sensitivity matrix. Okay. So this is a math behind it. Not a very difficult math. That math tells that this is how you find the change in the x. And if you know the change in the x, you add to original x, you find the new x. And you repeat this. You repeat this process. Okay. So having said that, are you okay with the speed, or please, some of you are good, we have to drag all of them, but that is how you represent with the change in the. So what you do is, you need to, what are the things that you need to know to solve this? To get delta x, what do you need? You need this and this. Okay, count on it. What is this means? Delta c. What does it mean? It means the change in the c with respect to f of x. What is f of x? F of x is a calculated power in our case. What is c? It's a constant power that we want to deliver, which is basically scheduled power. So this c is a number and this is a calculated power. So to do this calculated power, you need to calculate the power first. And then you find with a change in the number, then you get this. And then you also need this. So to calculate the power, you use the power equations and you divide the power equations into two parts. Classically, we call that as Vy cosine equation and Vy sine equation for the active power and reactive power. So you have to solve this equation at this. Then only you can start the process. How do you solve these equations? Do you know delta? Do you know V? Do you know Y? That's coming from Y bus. Do you know theta? That is coming from Y bus. The angle of it. Do you know the deltas and V? I don't know. That's why I wanted to solve, right? But I need to start. How do I start? You start with a number that you think is great. That number for a V is 1. The number for the angle is 0. Okay. That starting point for the power flow is generally called flat start. I don't know whether you have heard of this term. Flat start means starting at flat. Will the final voltage be 1? I don't know. Final voltage be 0 or angle be 0? I don't know. So you start from a flat start. If I do that, I can solve this equation. Okay. So once I solve the equation, I will be able to get this P and I can this one. Then I will be able to get this C. Then I can find the change as long as I know this, right? This one right here, I need a change or sensitivity written for the P and Q. This sensitivity matrix for the P and Q, I write it together in one matrix and that matrix is called Jacobian. Okay. So Jacobian matrix is a first derivative of the function with respect to the state variable. Okay. That function is P and delta, P and V, Q and delta, Q and V. So you write that, then you will get a Jacobian matrix. That Jacobian matrix, you write it. So how many delta you have? Depending upon the how many bus I need the delta to calculate. All the buses do I need to calculate delta? No. All the buses I need to calculate V? No. We told you what to do, right? Which bus what. So you write like that, then you get the Jacobian and you have to do the derivative. So derivative with respect to, oh by the way, this derivative is a special derivative and they are called partial derivative because you are not finding the changes one variable to the other in full. You are changing the one variable other in part, which means you are going to fix one variable as a constant and then find the derivative for the other variable. If you do that, you will get this math, and that math is basically you should be knowing. Once you know that math, you can solve the using flat start. You can solve the power flow. So, for example, for a 3-bus system, we can solve the power flow with the Newton-Raphson example. If we are excited and if we want to do this, we can include that in our problem solving session tomorrow. I can give you this example. You can solve this for Newton-Raphson power flow. No strings attached, meaning no grades and no problem, but you can solve it in the problem solving session or some other time. So that is how we solve the Newton-Raphson power flow. Good. Okay. So you can, let me just say one part here. So now you say, wow, that's too much. A lot of derivative I need to calculate and then solve it for entire power grid, a lot of work. So you can say that this P and delta is, we call it very tightly related. P and V is not very tightly related because the active power is not very tightly related to voltage in transmission network. Not true for power distribution network because of some other things called X divided by R ratio or some other quantity, which we will not be able to talk about it now. But in general, say they are not tightly related, so you can actually ignore them. This and this. If you ignore them, then you can solve it only on this. Okay, that is called fast decoupled or decoupled power flow equation. We are not using the coupling of these two. So what happens if I don't know this topic on power flow transmission system? Some of you, are you all able to follow what I was saying? If you don't know about this topic, don't worry. We will work on this topic part again one more time. That's something which you can at least think about in baseline. All right. So coming back, what do we have now? We have a knowledge about this right? Do I need to have knowledge on a distribution system how you solve the power flow? Yeah, I need to have some knowledge. Otherwise, I cannot uh, solve it. Integrated. Remember, integrated. That's the goal. Okay, so just talk about distribution system power flow. So distribution system power flow, you have a power supplying and power receiving, and they are coming through a distribution line, a switch or a transformer. Did you remember the modeling of transformer, which is tapped transformer, voltage regulator, OLTC? You remember the modeling of lines, right? Distribution lines, impedance. And you also know there are some switches that can happen on the distribution. And do you remember the name laterals? Yes. How many of you remember the name laterals? What is lateral? Did we talk about it? Yes or no? When? This morning we talked about baseline one. So the laterals are right here. So all these things you should be knowing. So now you can say there is a cogenerator. Cogenerator is a DER, shunt capacitor connected and the load connected. These three can be connected in one node. So you can represent the current, power and voltage. That's basically your distribution network. So if you wanted to represent the distribution network, there are some challenges. One challenge is this distribution line that you are going to see has to be modeled in each phase. Remember the transmission line when we are modeling resistance, inductor. One. Why? Because all the three lines you are going to say. So one representation is enough. Resistance, no resistance, you ignore. Then I have inductance. That was very simple. Here you need a resistance. Can you ignore? No, resistance are there in the distribution. I cannot. So you see one resistance in another resistance inductor, third resistance in inductor. Voltages or current flowing through each one of them. Are they balanced? No, they are not balanced. And I ignore the current in here in each one of them and then say they are balanced? They are not balanced. If they are not balanced, what will happen to the voltage in each of those lines? Voltage will be changing, right? If the voltage is changing, how do you represent the voltages? You represent the voltage by adding some capacitance effect on those lines to represent the voltage. So having said that, A, B, C and neutral, all these lines, three-phase, four-wire or three-phase? Everybody know three-phase, three-wire, three-phase, four-wire, three-phase, four-wire or three-wire? You will need to have this. So you got to represent them in the form of impedance plus the capacitance on diagonal element and cross diagonal element representation of the series representation of this three-phase impedance. And you got to represent A, B, C means what? Each phase. So one line, second line, third line. So there will be 2 by 2 by 2 matrix connected on each one of those lines to represent a one segment. Like that you represent for all the segments. So lines that are connected in series and admittance will be represented like this. Okay, so that's how you represent distribution system lines. That course is not on undergrad level, so I don't know, here distribution system course are mostly on the grad level, right? Advanced topic, it's not a undergrad level, so I don't think you. How many of you have seen this type of modeling for distribution system lines in your life anytime? No, this is something that is how we model the distribution network. Are you catching what is the difference between a general transmission? No, right? Yeah. So this is how you represent distribution system line models. Okay, so let's catch up with some key difference. What's the first difference? We represent each line. So it will be 3 or 4, depending upon that. That many elements will be there in your one line configuration, right? Second, you represent the of diagonal elements and diagonal elements, depending upon whether there is a series connection or we want to represent the dynamics or not. So that's a full detailed distribution line representation. If you represent the transmission line in a three-phase form, you represent the same way too. However, you don't have to because you don't have that requirement for the transmission line. Good? Okay. So the next one is voltage regulator. You can represent the voltage regulator in the form of Y, ABC for a regulator, with the R being the inverse of the tap for the regulator. So this is a three-phase regulator of voltage regulator. Okay. What do you mean by three-phase regulator? Regulator connected on each phase. Can you have a three-phase regulator with one single phase multiplied by 3? You know what I'm talking about? One single phase. I have a regulator or a transformer with a single phase. Okay, connected, right? You know, single phase transformer or no? One phase connected on two windings. One winding in one phase, another winding in other side of the same phase. That's called single phase transformer. Okay, and if you represent that three of them, they're called three single phase transformers with each line. Now you take all the three single phase winding and connect in the form of Y and delta. Do you know Y and delta? Everybody know it. To connect in form of Y and delta, you'll get three-phase transformer. Okay, you can have all the three-phase windings connected together. That's called three-phase transformer. So you buy a transformer from the market, you may get all the winding connected, all the three connected together. It's called three-phase transformer. If you have independent transformer connected and you are asked to connect it outside, that's called single-phase transformer. So you can represent single-phase transformer multiplied by 3 on all the three phases. If you do that, you will be able to see configurations like this. Each of those phases can be controlled or tapped, right? So that's basically your voltage regulator. And then you can actually have a loads connected in the form of zip configuration for the loads connected on each of those lines in the form of three-phase, two-phase, or single-phase. When you two-phase, you connected in Y and or in delta. I'll skip this part a little bit. This is how you represent the inverter based resources or DERs. Okay. So I will talk about this DER integrated part. There is another session, so we'll talk about that during that session. How do you run the power flow? One easy way to run a power flow is called forward, backward, sweep power flow. How many of you heard this word? Forward, backward, sweep power flow. Not that difficult. If you don't hear it, no problem. We will do it now. Forward, backward, sweep power flow means you are going to represent the voltage on the distribution network knowing the current. Okay. So how do you represent the voltage on a distribution network knowing the current? Oh, by the way, the voltage goes down on a distribution network all the way to the end, right? So I'm going to talk about, let's assume you have a 5-node system. You know, 5-node system, and you want to talk about 5 nodes. Each node has an impedance and loads connected in for at the end. Okay. The way to solve this is the trick what we talk about to solve on a distribution network. Oh, by the way, is this distribution network consist of the problem that we faced on solving power flow in transmission system? Remember the transmission system power flow, when we solved it, what are the challenges we faced? First, they are nonlinear in nature. Second, two equations and 4 unknowns, right? So here your goal is to talk about the voltages at each points, right? So what are the unknowns? Just the voltage on each point. So what you can look at to see what will be the voltage here and then calculate the voltage back there. So it's a 5-node system that we are considering. And how do you start? You start by taking the voltage at this point, the forward time, and this voltage you assume that there is no load connected. If there is no load connected, this voltage will be no load voltage, which will be assuming that as 1 per unit. Start from flat start. If you have a 1 per unit voltage, can you calculate the voltage here? Yes, you have a drop, you calculate the voltage. We have a voltage calculated here. Can you calculate the voltage here? So on the forward sweep, you compute the voltage at node 5 under no load condition. With no load current, there is no line current, nothing is flowing. So you run. Then in the backward sweep, commences computing the voltage load current at that node and then this current. So you know the voltage, you can calculate the current and then you go backwards. Okay. So to calculate the load current, you use this equation. You know this equation. Okay. S equal to VI conjugate. And then after you compute, you go to the node number 1. And once you look at the source voltage 1, you calculate the specific source voltage and you do this iterative sweep again. Oh, they are not linear in nature, but you don't have a problem of two unknowns and two equations because you are actually two equations and four unknowns because you are actually not running the generator side of the power flow. So we'll do maybe an example. Okay, this also will tell you something interesting. See this impedance here? 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the impedance between 2 points. How do you represent an impedance in a Y bus in a transmission system? 1 divided by Z12. 1 divided by 3 plus J5. Here, point 8, and why you have 9 of the elements? Because you are representing them in the unbalanced form for the entire matrix for the 3 phases. That's the reason you have 9 elements. 3 multiplied by 3. That's why you have 9. You see that? Remember this right here. I'm talking about this. When you look at this equation, you think it's very complex, right? A lot of things here. This is how you represent for one line. Right? How about this next line? Another equation. Okay, another 3 by 3. So you have a 3 by 3 matrix for 3 lines. 1, 2, 3. Why 3 by 3? 1 to 2, 1 to 3, 2 to 3. 2 to 1, 2 to 3, 2 to 2. Right? This is off diagonal and diagonal. So you have 9 such numbers here. Where do you get the number? Well, you can calculate this number. There are methods that you can use to it. So if anybody working on distribution network and doing power flow associated with that, this is how you should be modeling the distribution network. So you see this number, this is given to you on a power system to run that. So Z12 and Z23 are given. So what you do, you initially voltage are set up on this for the V1 right here, and this is standard voltage. You assume they are all the same, and the loads are defined in here, calculating the loads in 2 places. Oh, this load is a 3-phase load or a single-phase load? How do you know? Everything is 3. Okay, these are 3. Power distribution network power flow is 3, not 1, because we have 3. So is this a 3-phase load or a single-phase load? It's a one load, single-phase load, connected to only one phase. How do you know? Because the other two numbers are 0. Which phase the load is connected to? Phase B is connected to. A and C are not. How about this? All the 3 phases, they are loads. When you have a 3-phase load and single-phase load, yes, you have your home. When you have it, you have single-phase power, and your home, when you're in a commercial building, or you have 3-phase power. You follow what I'm saying? So this is how you see. Every time it will be 3 multiplied by 3, not 1 equation. Okay. So you find that the S divided by V. So in a standard circuit analysis, you can find the V out, V in minus Z I, and based on that, you can do the backward sweep. So you go back and calculate the load divided by the voltage, calculate the load divided by the voltage, you get the current. From the current, you add the load to, you get the power flowing in the I23. And from the power flowing from I23 and the load connected, you can find I12. Now, if the node 1 is the last node that you have, which is a head end, you stop right there. After you stop right there, what will you do? You calculate the voltages. So this voltage is 2400, this voltage is fixed. Then you try to calculate the next voltage, you get the next voltage. find out the difference between the first voltage, first time we use this voltage, then you iterate, get this voltage. Is a difference zero? No. So there is a difference. That's error there. So what you do is you take that new voltage, continue to calculate the V3, find the difference. After you find the difference, if it's greater, you repeat to calculate V1, V2, V3, take in each iteration and finalize the voltages on every time. This is called, I just storyboarded quickly. You will have a problem solving session and you can solve it, by hand. So you calculate, look at the error and then finalize error and then you keep doing that. And such way of solving the voltages on a distribution network with the power flowing is called forward, backward, sweep. How many minutes we have now? We're almost done now. So when we come back, we're running a little behind. I wanted to talk a little bit about the integrated power flow. So what we will do is we have to buckle up for tomorrow to start a little bit faster on a fast space. Then only we can get to that. Because our goal for this was to do the integrated. So how do you do it? Maybe can I have 5 minutes maybe, everybody? Yes. Now we found a way to solve the power transmission network through a power flow called Newton-Raphson, right? We found a way to solve the power distribution network through a power flow called forward backward sweep. We will do these two power flow when we come back tomorrow as a tutorial, right? What happens if you have to solve the power grid with the distribution system and the transmission system together? Okay, what do you have to do? You have to run the transmission system model, then run the distribution system model, run what? Power flow, and then connect them together, right? So I'll take 5 minutes to explain to you. It's actually more than 5 minutes, but I'll take 5 minutes to explain to you how this process is done, and then maybe we can do a small example to illustrate the process. Okay. So there are two steps, very critical step to do this, to solve the problem. You understand the problem? Transmission system, distribution running together. One challenge in this is that the transmission system is running mostly using the models, we call it positive sequence representation. Distribution system is running in three-phase representation. So you have to stand where? Sequence or phase. If you want to combine them, you have to run them together, right? So we will find a way to solve them together. There are two different approaches. One approach is called decoupled, meaning you run the transmission system power flow, then run the distribution system power flow, and then connect them. The other one is you combine them together, and one run as unified. Okay? So I'll talk about the first method, decoupled. Okay? So there are two different things you need to do in the first method. First method is to represent the distribution. Let me talk about the method first. So this is a method. You run the transmission system power flow, right? How do you run the transmission system power flow? Do you remember how to run the transmission system power flow? Right? What do you use to run the transmission system power flow? What method you use? You just learned. Newton-Raphson power flow. You run the transmission system. Once you run the transmission system power flow, you run with this. Okay, all plus means that, right? See that? After you run the transmission system power flow, what will you get? What's the output of the power flow, by the way? Hmm? What will you solve if you solve a power flow? Solve for the states. What are the states in a power flow? What will you solve for the you solve for voltages and angle of the voltages, right? These are the states in the power flow. So you solve for voltages and angle of power flow, then you calculate the power, then you calculate the losses, then you calculate the power flow. All those things are unwinded if you know the voltage and angle of voltage, right? So after you solve this power flow, what will you get? Voltage and angle of the voltage. That voltage and angle of the voltage you take. Take for what? For the power distribution system. Where will that voltage and angle of the voltage go? That will go as a voltage for the substation for the power distribution system. Remember the voltage V1 we call 2400, 0, 2400, 120. That number, where do you get that number? This is the number. So you take that number and go to the distribution system power flow, run the distribution system power flow. Output of the distribution system power flow will be power, active and reactive power from the substation. Take that active and reactive power from the substation, put this as the load in the transmission network. This is the load that is connected to the transmission. Then you run the transmission system. Are you following this? This is how you run, and you stop when? You stop when this voltage that you, this power that you send it out, and then the voltage that you calculated between two iterations are small, they are useful. This is called decoupled power co-simulation, or what you call it, integrated transmission instruction. Good. So you can solve this. One thing which is important to do that is you should know this power. How many distribution systems are connected at this point? You don't have an idea. Only know is a power on that spot load, right? If I have a distribution system connected at 5 megawatt, on a transmission end it may be 25 megawatt, 30 megawatt, because there will be multiple distribution system connected, right? So what do? You got to come up with a method to aggregate the distribution system power to the transmission system power. So the transmission system is representing 14.9 and 5 J. Distribution system is 3.6 and 1.4. You have to bring this distribution system to 14.9 and 5. How do you do that? You aggregate them, multiple distribution system. You have 6-7 ways to do that. One way is to take the power distribution system network full, then you multiply it by a constant, saying that that's how the power changes on distribution, how many distribution network, then match with the total load on the transmission network. So we'll see. If we get tomorrow sometime on the tutorial time, I don't think we'll have time for 3 Newton-Raphson backward, forward, and this. Maybe we'll give maybe one small problem and then. Yeah. So let's assume transmission system load is 10 megawatt and 5 Q. Okay. So if the distribution system representation is only 3 instead of 10, there are 7 ways to do it. But in nutshell,
My question is, it will come exactly to the same value. Means
then you don't need to worry. Oh, you need to have exactly the same value? Yes, you must have exactly the same value, because the transmission system power flow is using that load on that. If they won't come exactly the same values, you will get a transmission system power flow for another value, which is also okay. But so that's a very good question. So you have a transmission network and you are modeling the transmission network for power flow considering some spot load, right? If that spot load is different, then you are solving the power flow for another condition, not the same condition. Now, normally people don't solve the power flow with different spot load condition. You take the entire spot load and you multiply with a scalable number like 3 times, 2 times, because the load and each point in a network is not changing. It is only changing together like a load variation. So spot load into a different number, if you change, it's a different operating condition. Now let's assume that in the iterative loop you keep changing this. Then it's chasing the goose. You will not be able to get the same operating condition all the time. So you cannot do that in the integrated loop, considering that spot load is different all the time. So that's why we need to reach at that same load condition with the given distribution network. But at the same time, you cannot run 15 distribution network along and representing the transmission network. That's too much, right? Complexity. So what you do is you run one distribution network and then say that it's a duplicate copy of that to get that number. Are you following what I'm saying? So inside the loop, it's not allowed to change. You can change it at the beginning and keep that condition all the time. Other questions? Okay, so I think tomorrow we will start talking about the optimal power flow. We will be keeping one time to run the power flow. Maybe same example I will let you run, so you'll get some idea how it's been done, and maybe an integrated example for a 3-bus, 5-bus connected to 3-bus, something like that. So hopefully you will get an idea about co-simulation. And tomorrow when we'll start about optimal power flow, and we'll go into a different world a little bit on optimal power flow, and we talk about how you consider cost into the mix and how it's connected with power flow and the differences. So that's basically for tomorrow's topic. In between, if you have any questions or if you have anything that you are not able to understand, or if you have any suggestions to add that you are working on a topic or a study that you want me to include and talk a little bit about that, bring it over. There is no guarantee that I will include everything inside the session time because of the time we are talking, but I can give you extra ideas or talk offline. Good. Okay. This is for you, by the way. So take the most advantage of whatever you want to get out of this. So I'll be able to give you whatever you want. Not all the questions can be answered with my capacity, but I will try as much as I can. All right.
Thank you, sir. Thank you for your systematic approach. You have explained step by step how to go for the power flow analysis for transmission as well as distribution systems. So this is the basically building blocks for doing all optimization kind of thing that will be discussed in tomorrow's talk. So thank you, sir, for this nice discussion in this session. Now this session is over. All the participants are requested to again rejoin the session tomorrow sharp at 9:30 am. So again we will meet tomorrow. Thank you all for today.